Hi guys, welcome to assignment 1 for COSC330 530, and in assignment 1 you're going to be cracking an AES cipher and building a program that searches for the key that's used to encrypt some plain text to ciphertext. So you're going to be implementing a partial key search. So if you're unfamiliar with the concept of encryption, essentially encryption provides us with a means to communicate securely through an insecure medium, such as a network like the internet. So we start off with some plain text or some basic data, and we apply an encryption operation to produce a garbled ciphertext version of that. And typically that operation uses some sort of a key to implement to produce the ciphertext, and ciphertext is what we send through our insecure medium, and then at the other end we perform the reverse of that operation using the same encryption key to retrieve the plain text, and it allows us to create our own secret channel of communication. Now, these algorithms are designed so that it takes a lot of energy to basically brute force break the encryption and work out what this key is. And so you're going to be writing a program that breaks the encryption and finds the full key for the advanced encryption standard. So your program won't have to find the entire key. You'll only be searching for part of the key. In fact, I'll give you all bar the last 3 bytes of the key, and your program will need to search through testing plain text ciphertext pairs to work out the value of that key. So although that might sound daunting, most of the implementation stuff is already included in the files in the sample code that I've dropped into the assignment here. So the first piece of sample code, the first starter code item, is a program that demonstrates the encryption process to generate some ciphertext. So if we jump onto Turing here and bring up our generate ciphertext example, you can see it's just a simple C program, has a usual set of C headers, and we've also included these OpenSSL libraries. So these are installed on Turing. They're part of the OpenSSL libraries that most programs will use to implement encryption, and they provide all of our encryption and decryption functionality. If we scroll down through, I've got a couple of functions defined here, an initialization function and an encrypt function. We'll come back to those later. But if we look at the main function here, we start by creating an encryption and a decryption object, and we read in. The first thing we really do that's relevant to us is we read in our plain text and we store it in a local variable. So in this scenario, we're just reading into a buffer of fixed length. We then go through and we read in the key that we want to use to encrypt that particular plain text file. So we go through and we read that off the command line using our argv data. So we read that in through argv, and then we go through and we call our encryption function. So this AES encryption function that I've supplied up here, and it's really just a wrapper for the library function that's provided by the OpenSSL libraries. And we see we initialize our encryption, our encryptor device, and then we go through, pass in the ciphertext, so our pointer to our ciphertext, which we've allocated up here using malloc. We pass in our plain text and our encryptor that we've initialized with our key, and we go through and generate the ciphertext that we'll need. And then all we do is punch that ciphertext out using printf. So if we jump onto our terminal here, if we go through and have a look, you can see here I've already downloaded this code. I've even given it a test, but we'll go through and we can quickly go through and compile our code. So if we go, and the command to compile it is supplied in the assignment here. You can see my command line arguments here in the description. Oops, that's not what we want. There we go. But here you can see that we're just using the GCC compiler to compile our generate ciphertext.c file. The only tricky thing that I've got in there is the -l crypto flag, which tells the compiler to include the OpenSSL cryptography libraries, and we're generating a program called generate ciphertext. And because we're good computer scientists, we've got the -wall flag, which will warn all during the compilation process. And you can see it's compiled, but it's just delivered a couple of warnings. And I've left those warnings in there on purpose because they're little simple mistakes that I want you to go through and correct. So if you're going to use these snippets of code and functions as part of your final solution, in order to get the full marks for the assignment, you'll need to work out why those errors or those warnings are occurring and go and straighten them out. But we've compiled our program, so now we can go and we can generate our ciphertext. So if we go through here, you can see I've got an example where we go through and we call generate ciphertext using a simple key. We'll drop that into here. So our simple key is just the sequence 1, 2, 3, 4, 5, 6, 7, 8 4 times over, and we're going to pipe the output from our program into cipher.txt. When we run that, not a real lot happens. There's no output. We've got our cipher.txt there. If we go and open cipher.txt, you'll see that it's all just non-printable characters, except for a few in there that you can see. But it's basically our garbled ciphertext that we would normally send through our insecure medium. And so that brings us to our next example, which is the decryptor. So if we jump back to the assignment, we can decrypt our text by performing the reverse process using the decrypt example. So if we jump back onto here, let me go and open that one up. Decrypt.c. If we bring that up into Visual Studio Code, again, the same series of headers included. This time we have an AES decrypt function which wraps around the OpenSSL library calls to perform the decryption operation. And again, we go through, we read in our ciphertext, we read in our key, and we perform the AES decrypt function. So if we jump back in, we have an example on our assignment description here of applying the decrypt operation. So I've already compiled that one. You can compile it using the same command that you used to compile the generate ciphertext. And when we run through and do that, you see we get our usual array of warnings, but the code has actually compiled. And when we run that, we should be able to retrieve our plain text. And you can see we've read in our ciphertext and we've printed out the plain text that's in our file. If we change our key, if we make a mistake with our key, for example, you can see that we can't decrypt it. So when we perform the decryption process using an incorrect key, we just get more garbled ciphertext coming out of the decrypt operation. So that just gives us a basic idea of how to encrypt and decrypt the information from a text file, and you're free to use any of the functions and any of the approaches that are in that as part of your assignment. But the main example, the really important example that I've provided, is a program called search_keyspace.c, and essentially it takes both the plain text and the ciphertext file along with a partial key and searches for the remaining bytes in that key. So if we jump back here onto Turing, and we can see that again we've got our usual array of OpenSSL libraries alongside our usual C libraries included, and we've got our decrypt function, our initialization function, and our main function down here that we'll need to implement this operation. So we read in both our ciphertext and our plain text. So remember, we want to find out the missing bytes from our key, so we need an example of both the plain text and the ciphertext to which it maps to do that. And we also read in our partial key. So we read our partial key from the command line using argv up the top here. And the first thing we do, so remember we're only working with a partial key, so there's going to be some missing bytes. So the first thing we do is we pad the key out. So if we have 3 missing bytes, we need to move that key 3 bytes to the left, so that we can create the section that we're going to search for. So we do that just in a simple loop here, where we work out how many bytes we have and then pad the key to the right by that number of bytes. Now, the second series of operations look a little bit more daunting, but the idea with the next piece of code is to work out how we're going to increment and search our key, search for our missing key, the missing bytes in our key, and we do that by focusing on the bottom 8 bytes of the key. So this program can only search for a maximum of 8 missing bytes. If we want to search for more than that, we have to modify it further to do that, but if we're searching for that many bytes, it's going to take way too long. So we're just going to search for no more than probably 3 bytes of missing key. And so we start here, if we only want to focus on this last segment of our key, so in this case the last 8 bytes, we start by declaring an unsigned long integer, which gives us 64 bits or 8 bytes of space, and then we take the bottom 8 bytes and we pack it in to that long integer. So we take each of these 8 bytes. So we take, for instance, the byte at position 8 from the right, and we move it up to the top of our kilo bits long by bit shifting it 56 bits to the left. And that essentially packs it into the top section, and we do that for each respective byte that follows, right down to the last byte in the key, which doesn't need to be shifted at all, and that creates a long integer that we're going to work with. Now, once we've got those low bits, or that last 8 bytes of our key, we can then start searching our key space with that. And you can see here we have this for loop, this counting loop, and it runs through, and by performing an OR operation with that kilo bit, so the last 8 bytes of our key, we can essentially test all of the different combinations in there. And this loop is the part of this program that you will need to parallelize with your code. And once we've done the bitwise OR with our kilo bits, we then reassign those low bits to the last 8 bytes of our key array here by reversing the operation you saw up above, and then we initialize our decryptor and apply the decrypt operation, and then just use string compare to compare our known plain text that we've read in from our file to the plain text that's come out of our decryptor. And eventually, provided that there is a solution to this, you'll get some plain text that will match the plain text that's passed in, and you'll have found your encryption key. So really, the focus of this assignment is to parallelize the processing that's going on in this for loop. So we can run out and we can compile that program. So if we go through, we can compile it using the same approach that we saw before. I've actually got a command sitting here. So again, we're just compiling keyspace search.c. We're including the lcrypto flag because we're using the cryptography libraries. And when we do that, we've got a bunch of warnings. Again, if you use code snippets out of this, you can go through and correct those warnings. Another thing to be aware of is I've got missing comments, and I've got commented out code, and I've got inconsistent tabs and all sorts of formatting errors in there. I've left them in there so that you can work on those to remove them as part of your exercise. But if we run through, we've already created our ciphertext using our generate ciphertext program that we compiled before, and we can use search key space to go through and find the key. So you'll notice here that I've dropped 1 byte off the end. So it ends in 1, 2, 3, 4, 5, 6, 7, and the 8, the byte that represents the 8 is missing, and our program has gone through and it's worked out the value of that last byte. And if we drop off another byte, again, it can go through and search that, and it's doing that fairly quickly, but when we drop the 3rd byte off, you can see that it pauses and it takes slightly longer to find that. And if we drop off another byte there, it'll take even longer. It'll take too long to demonstrate in this video to find the key. So my program is exhaustively searching through all of the combinations of keys until it finds one that allows you to map the input plain text to the known ciphertext. And essentially that will allow us to work out the key. So if we jump back to our assignment here, so your program will parallelize that whole process. So you'll be using a multi-process program to implement that. So you'll be forking off processes, and each of those processes needs to go and work on its own piece of the key space to hopefully find the key. So you need to divide that up, and you'll need to communicate that key back to the original process. So you'll have your main process or your parent process spinning off a bunch of worker processes, and they'll need to communicate that key back to the parent process using you can select from any of the interprocess communication systems that we look at in this first module. So you've got pipes, FIFOs, you've got memory mapped files, and you can go through and use any of those that you wish. So I've provided you with some example plain text and the known ciphertext from that, and I've given you a partial key. So the partial key is missing 3 bytes. Of information. So there's 3 other characters in that key that you can expect to find. And you can go through and run using this ciphertext and plain text linked here. If you put that partial key into my sequential key search example, it will find a solution for you. It takes about 5 to 10 minutes depending on the load on the system, but it will do that, and you might want to do that. It's probably a good idea to do that first up just to find out what the key is, so that when you're testing and playing, you know what you're looking for. So some hints and tips for this one: make sure you review all of the sample code, go through and compile it and play around with it, review the interprocess communication methods and select the one that you believe should work the best. You can use any one you want, as long as you pick a method to communicate that key back to the main process. Make sure you use the data display debugger when you're programming, because it'll allow you to view what's going on in your variables and spot errors. So it's especially useful when you're looking at your keys, so you can work out if your key search is producing trial keys correctly. And pay attention to the marking scheme. So there's quite a comprehensive marking guide that goes with this assignment. As you can see, most of the marks are in the top section here, where we want your solution to compile and run and actually find the key. We want you to achieve parallelism, so we want a multi-process program on there, and we want to make sure that you're communicating your key back to the parent process correctly. And then we want you to write code that doesn't produce errors. It's got it's nicely tabbed and has nicely formatted and tabbed, and has appropriate appropriate comments and documentation throughout. So we want to see header blocks at the top of your functions that explain what's going on in your program. You should also include a make file with run and clean targets, so I can build your program and test it all out really quickly. So you've got a fair bit of, you should treat all of these items as check items, and you've got a fair few of them to go through to make sure that you get full marks in your assignment. So it should be a really cool exercise. Again, by using the AES encryption standard, it sort of gives you an idea of an industrial strength encryption algorithm and how difficult it is to break. So your program should take at least a few seconds it'll still take a few seconds even if you parallelize it to find the key, because there's lots and lots of combinations to test there. So good luck with your assignments. If you have any questions, make sure you post them on the forum or email through, and good luck on your assignment.